Hello there. Welcome to our Geo for Good Lightning Talk series. This month marks our third round, and the theme this month is air quality. My name is Karen, and I'm a program manager on the Google Earth Outreach team. Earlier this year, we started a series of monthly lightning talks by and for nonprofits, scientists, and other change makers who want to leverage mapping tools and technology for positive impact in the world. We hope these talks will inspire you to think of new ways that you can have an impact with mapping tools or provide operational or practical hints to improve and optimize your workflows. I'm very excited today to welcome this month's speakers, Michael, Cristina, Ashley, Burj, Meg, and Lauren. Welcome, you guys.
Hey, Karen.
Hello.
Thank you so much for joining us. It's great to have you all here. So before we kick off the first presentation, which is going to be Michael, I would love to call everybody's attention, everybody who's listening out there, call your attention to two different things. The first one is the live Q&A feature. If you're watching live, you can look below me and you'll see a Q&A section, and you can write your question in the Q&A section. If you have a specific question for a specific speaker, be sure to identify which speaker you want to ask it to, or if you have a general one for all of them, you can leave it open too. Second is the link to the slides. So we've shared the slides if you wanted to open them up either during or after at a later date to get a better look at some of the slides, you can definitely do that. And you can find that below right in the resources section as well. All right, great, let's begin. So the first person we're going to hear from is Michael. Michael Heimbinder is the founder and executive director of HabitatMap. He is an information designer, a community organizer, and an educator. Since launching HabitatMap in 2006, he has worked with dozens of community-based organizations and schools to create planning and advocacy maps that publicize the issues they care about most. Let's hear Michael's talk.
I'm going to discuss how community-based organizations can use community science to clear the air. Here I quote Margaret Gordon, co-director at the West Oakland Environmental Indicators Project. The finding that Black people suffer more from freeway pollution is something we've been living and looking at for years, she said. The evidence is found in the crevices of people's ceilings. It's not dirt, it's particulates. Here I quote Dariela Rodriguez, Director of Community Development at the Point CDC. Young people came back from monitoring air quality with AirBeam saying, it smells, it's toxic, I don't feel good. The infrastructure in our community tells them every day that they don't matter. Here I quote Margaret and Dariela to emphasize the problem is not that the impacted community is not aware. They see it in the cracks of their ceilings that are full of particulate matter. They see it when they look around their community and they see all the noxious infrastructure located in their community. And they experience it when they have to stay home from work to take care of a child who's sick with asthma. The problem is that the wider community is either not aware or does not care. The solution that HabitatMap offers is one, easy to use, open source, free and low cost tools for recording, mapping, and sharing accurate air quality measurements. The picture on the left shows folks from the Brooklyn Movement Center and the New York City Environmental Justice Alliance holding AirBeams, which is an instrument we created for measuring fine particulate matter, and Android phones running the Aircasting app. Two, the solution is analyzing and presenting the data in a clear and compelling manner. Many of these campaigns will end up collecting hundreds of thousands, if not millions, of air quality measurements. And they need to find a way to present that data in a way that makes sense to folks and can be shared with a wider community. Three, and most important, the solution is grassroots advocacy. There's no such thing as a one-size-fits-all solution, and the most effective solutions come from the communities most directly impacted. So community in the South Bronx choking on diesel exhaust from trucking-intensive operations like warehouses and waste transfer stations is going to be in pursuit of a different solution than a fence line community in Louisiana's chemical corridor dealing with the expansion of a petrochemical plant. And last, but really most important, education, capacity building, and network building are key drivers of social change. You've got to educate young people and adults in the community about the health impacts of breathing poor air. You've got to build the capacity of these community-based organizations to undertake this work, to take air quality measurements, to interpret the data, and to share it out. And you've got to build the networks between organizations that have common cause and between those organizations and, say, academic institutions that might be able to do data analysis and government institutions that are ultimately responsible for implementing policies that can clear the air in these communities.
Thank you so much, Michael. I've always loved hearing you talk and hearing about HabitatMap's growth over the years. I had a question just to kick things off, and then we'll take live questions in a little bit for you. On your website, habitatmap.org, people can view a map which includes the fixed measurements from air beams, mobile measurements from air beams, including, they can look at individual sensors and how they change over time, as well as aggregated data over time. So a lot of powerful visualizations in that map. Can you give us an example of how a community organization, either a community or a nonprofit organization, have used this map, either online or printed potentially, for advocating for a policy change in a city or a community?
Absolutely. It's a common question because people really want to know, I'm collecting all of this information, how can I actually use it to make positive change in my community? So there was an example from a few years back. We were working with 3 different community-based organizations here in New York City. One was the Point CDC in South Bronx, El Puente in the south side of Williamsburg, and Uprose in Sunset Park. And what we did is we worked with those communities through the New York City Environmental Justice Alliance and trained young people on how to take air quality measurements using the AirBeam and the air casting platform. And we also trained them in how to count traffic. And so we had them set up at trucking intensive intersections in each of the neighborhoods. And they did it during the morning rush hour and the evening rush hour. And they counted trucks and they classified those trucks and they simultaneously took air quality measurements. And the drive behind the campaign was that many of these communities have lots of waste transfer stations. So garbage gets picked up from residential businesses and gets dropped at these facilities and then loaded onto big 18-wheelers to be trucked out of the city, primarily to be buried in landfills in places like Pennsylvania. And so we wanted to know how many of these trucks are waste transfer station trucks and how many trucks, period, are coming through these intersections. And then do we see a difference between the measurements we take at these intersections and the measurements that are coming from the state-run monitoring network? And what we saw was that during these periods of time, sometimes it was like a truck every 10 seconds. And so you just had a tremendous volume of trucks. And the emphasis behind the whole campaign was that New York City was considering something called garbage zoning. And so instead of somebody, a private carter, coming and picking up from some businesses in Greenpoint and then traveling over to Manhattan and then traveling over to Queens, literally the routes that private carters take in New York City to pick up garbage are miles longer than they should be. And so the city adopted something called garbage zoning, which will basically consolidate private carting routes that pick up garbage from businesses and make them a lot shorter and a lot more efficient. And part of the reason that the city decided to adopt this was because of the research that had been done by these community organizations. So it's a great example of communities learning how to take these measurements, learning how to do the analysis, presenting it to local elected officials, and then using it to drive a specific policy change. In this way, transforming the way that New York City handles private carters and solid waste.
That's great. Thank you. Thank you for sharing that example. That's wonderful. Wonderful. So thanks again, Michael. Our next presenter in the lightning round will be Cristina. Cristina Vrinceanu is a PhD student researching offshore natural hydrocarbon emissions using satellite imagery and innovative algorithms. Cristina is also a volunteer for STEAM activities, open data and open source, capacity building, and equality and diversity in geospatial. Let's hear Cristina's talk.
Hello, everybody. My name is Cristina, and I'm going to talk about mapping pollution during the COVID-19 lockdown using Google Earth Engine. I'm a PhD student with the University of Nottingham and not an atmospheric scientist. So mapping pollution has been done many times during disasters, such as hurricanes and other disasters, and it has been an obvious step to do when the pandemic hit in China. But China is a great polluter, so we've been obviously looking at that. And then we looked at another polluted area, which is north of Italy, the Pianura Padana, a place that is also very much polluted. So at the beginning, I've seen many examples on Italy, and when I tried to mimic what these examples were doing, I thought it's a very good idea to start with Google Earth Engine. So I'm not an atmospheric scientist, and I thought it's very interesting to use newly added Sentinel-5P data in Google Earth Engine to map the differences between 2019 and 2020 in Pianura Padana. And while I was doing this exercise for myself, I was also documenting it. So it turned out into a tutorial, and I meant it for beginners, for total beginners. And I also meant it to be used afterwards and build on top of it. And I successfully exported it to a Romanian use case. So this is the Romanian use case. We embedded it in a bigger platform mapping COVID statistics. We had the same functionalities as the original app, such as panels containing more scientific background, links for more information, legends, layer controls, some other locations, some statistics panel, and also a nice visualization of 2019 and 2020 with a slide bar, and we've used Sentinel-5P data in near real time, so it was updated every single day. After this, I've seen many other scientists, either at beginner level or more seasoned, that have done their own application. It was really interesting to see how each of them had a different approach. But what I really achieved with this tutorial and application is the fact that it got picked up by major news outlet in the Netherlands. It got also built on top by Justin Bratton and made like a very nice further application. It got picked up by a project in Myanmar that used it for mapping pollution in Yangon. And other people learn how to use Google Earth Engine based on this tutorial and application. So I really hope that you start with Google Earth Engine and you start playing with the data, and this kind of application for a total newbie helps you. Thank you very much.
Thank you so much, Cristina. You're absolutely right. When I first saw your tutorial way back in March of 2020, I was blown away. Your tutorial is indeed very accessible to users who are new to Earth Engine, who may not be JavaScript experts or Earth Engine experts. You mentioned that you yourself were not an Earth Engine or JavaScript expert before the experience. I'm wondering if you can share some learnings of that learning curve, if there were any obstacles that you faced, how you fixed them, and if you've done anything since, especially around the offshore emissions that the natural hydrocarbon emissions, or if Earth Engine is useful for you in that way.
Thank you, Karen. So yes, it's been a very steep learning curve. When I did the tutorial, I had some experience with Google Earth Engine, but very little. We've been using it for other applications when I did an internship with the European Space Agency. So during that time, we had some trainings, and I've been using it for other applications. But I'm not an atmospheric scientist, so I've never played with atmospheric data. And it was a first. And since I've seen that it was in Google Earth Engine, I thought, oh, this is a good idea. I started to work a little bit more, and I come from a Python background. So I think the learning curve, the most obvious one, was on learning JavaScript. And now it's much more easy because there are so many wrappers around Python, and there are so many libraries and things being developed for Google Earth Engine, which has like an amazing community, scientific community behind it. So I think that was the main step. And I know many people that might know another language, another programming language, but it's very difficult when you have to adapt it to something else. So those building blocks in Google Earth Engine were also meant for somebody that wants to transition in a way or another. I do use Google Earth Engine quite a lot nowadays. So basically, it's one of my primary sources for taking some data. And I use it in collaboration with Google Colab, which is another Google product, just to apply analysis on big, large data sets, and mainly for what I do right now, hydrocarbon pollution, offshore hydrocarbon.
Nice. And that's using the Python part of the Earth Engine?
Mostly.
Yeah, cool. Wonderful. Thank you so much. Awesome. Okay, great. Our third talk is going to be Ashley. Dr. Ashley Collier-Oxendale is an air quality specialist for science and technology advancement at the South Coast Air Quality Management District. Her work includes the analysis of data from low-cost sensors and building tools and resources to support engagement and participation by the public in air quality research. Dr. Collier-Oxendale received her doctorate of philosophy in environmental engineering from the University of Colorado Boulder. Let's hear her talk.
New technologies are enabling more members of the public and communities to collect air quality data. However, effectively making use of this data often requires a technical or scientific background. Here, I'd like to show how maps can support data visualization and interpretation for communities, and I'd like to highlight capabilities that it would be valuable to make more accessible. So just in case anyone is unfamiliar, here's some quick background on air quality sensors. These devices tend to cost anywhere between $100 and a few $1,000s. They're available for particulate and gas phase pollutants, and they utilize a range of operational setups. At the South Coast AQMD, the Air Quality Sensor Performance Evaluation Center, or AQ-SPEC, conducts testing and publishes reports on the performance of commercially available devices for the public. In 2016, the South Coast AQMD was awarded a Science to Achieve Results grant from the US EPA, and we worked with 14 communities throughout California to deploy approximately 400 sensors. This project included a series of workshops with each community, at which results were shared and discussed. And the following are examples of data visualizations that incorporated mapping to effectively communicate observations from these sensor networks. In this first example, an unexpected trend was observed in the ozone and NO2 data at one site. Leveraging the Google Maps platform to explore potential sources of emissions and temporal traffic patterns offered insight into what may be driving this trend and illustrated how mapping platforms can be sources of valuable contextual information. In many instances, pollutant concentrations were mapped using color scales to illustrate the spatial variability of pollutants. In this example, mapping the data helped to answer a question the community had asked regarding particulate levels at a specific site in their network. In this next example, incorporating a map into the data visualization helped community members to more quickly understand the relatively complex analysis shown, depicting the decay of pollutant concentrations near a source, thus illustrating how maps can support data communication to a non-technical audience. In this final example, different types of information were merged, including spatial, wind speed and direction, and pollutant concentrations, to effectively tell the story of an air quality event, in this case, 4th of July fireworks. All of these examples were shared during workshops, either in presentations and/or printed infographics, and they help to facilitate discussion and an increased understanding of local air quality trends by the participating communities. And I'd like to close by highlighting how making the ability to merge spatial information with other types of data more accessible could empower individuals and communities to not only collect air quality data, but also use that data to effectively inform actions that reduce exposure or emissions. And we're looking at a couple different ways to do this. So with that, I'll finish, and my contact information is here. Please feel free to reach out with any questions or comments. And thank you.
Thank you so much, Ashley. That was wonderful. You highlighted several different ways that map visualizations are helping communities communicate air quality. I noticed that in almost every example, a map was paired with a type of data visualization, whether it's a time series or bar graph or whatnot. In your experience and through what you've seen, can you help me understand, can you identify the top 2 to 3 visualizations that could be paired with maps and to help communities understand and communicate their findings and what that gave them as additional information paired with the map?
Sure, that's a great point. So as you might expect, in general, we found that simpler is better. So using a clearly labeled time series to illustrate a temporal trend, or a bar chart to illustrate absolute values, or a scatter plot for comparisons. We did try to use more complex visuals, and we shared and discussed those with community members, for example, polar plots. But those were found to be much more difficult to interpret and less intuitive to understand. So ideally, you want bringing together the map and plot should be breaking down the results of the observations into smaller pieces. So ideally, you want to be simplifying that information as opposed to adding complexity.
That makes sense. That makes sense. Like giving it a new lens, but not making it too complicated, adding value.
Exactly.
And complementing it. Yeah, that's great. Thank you very much.
You.
All right. Our 4th presentation is going to be from Berj Bogosian. Berj is an air quality specialist for science and technology advancement at the South Coast Air Quality Management District, just like Ashley. He's from the same location. He is responsible for the design, development, optimization, and implementation of mobile platforms that conduct mobile measurements of ambient air pollutants using air quality sensors and regulatory grade instrumentation. Berge is involved in the development of methodologies for hyperlocal air quality mapping and the management of measurement data using mobile platforms. Let's hear Berge's talk.
Hello, my name is Berge Dupuy-Todd, and I'm an air quality specialist at the South Coast Air Quality Management District. I will be talking about hyperlocal air quality mapping, air quality sensor testing, and data gaps between air monitoring stations. The South Coast AQMD has 42 air monitoring stations. High costs hinder the scalability of stations, which create areas of data gaps where there are no instruments reporting air quality data. The goal of our work was to develop a mobile platform on which to test air quality sensors while also performing pilot hyperlocal air quality mapping. We aim to utilize the mobile platform to fill in the data gaps and to develop a performance evaluation protocol for testing air quality sensors deployed on the vehicle. In a pilot collaboration project with Google Earth Outreach, AQSpec developed and integrated an air quality mobile platform inside of a Google Street View vehicle. The mobile platform was an integration of equipment and analyzers capable of accurately measuring these listed pollutants in the ambient air while the vehicle is in motion. Here is a map of the South Coast Air Quality Management District, jurisdiction, and the layout of the 42 air monitoring stations. With the data gaps in mind, we designed 9 unique mobile platform test routes to span across the majority of the jurisdiction while filling in those data gaps. Additionally, we designed the routes to include street-by-street hyperlocal measurements of California Assembly Bill 617 environmental justice communities. Further, the test routes were designed to allow for repeated sampling of a wide range of concentrations of multiple pollutant types. The repetition in testing allowed us to perform spatial-temporal comparisons between tests and test routes. Here you can see how we used Google My Maps to design each unique test route and a couple of examples of how a test route design can lead to different mapping types. After the pilot collaboration project with Google Earth Outreach, AQSpec published the Sensor Performance Evaluation Protocol. Utilizing this protocol, AQSpec will be conducting systematic evaluations of sensors on a mobile platform to generate evaluation reports. Consumers can read these reports, select the sensor that best suits their needs, and over time, contribute to populating the data gaps with sensor data. Lastly, this map shows the locations of existing air monitoring stations and stationary air quality sensors, clearly showing the continued abundance of data gaps in the region. Utilizing a mobile platform, AQSpec would like to explore and conduct mobile surveys in those regions to assess the needs of deploying additional sensors for air monitoring stations. As more sensors are deployed, either stationary or on vehicles, more data availability helps contribute to effective hyperlocal and regional spatio-temporal data analysis. Thanks for your time, and please feel free to contact me with any questions.
Thanks so much, Berge. I think it's very exciting to see that low-cost sensors are being tested in a mobile environment in this way. And so thanks for sharing some of the operations and methodology that went into this. What were some of the challenges that you and your team faced when you started mapping the resulting air quality data that you measured from the cars and the mobile platforms?
A challenge with mapping air quality sensor data on a mobile platform was the time interval that the sensors report. The onboard analyzers and equipment, those were reporting every 1 to 3 seconds, while the air quality sensors had a much longer time interval. So because the vehicle was in motion and sometimes traveling at high velocities like on highways, that meant that there could have been significant distance between each data point reported by the air quality sensors. So combining that challenge with the challenge of time synchronizing, the sensor data to the analyzer data, that meant basically we had to come up with some post-processing methods and QA/QC methods, and just ensuring the air quality sensor data was accurate on the map, both location and value. And another challenge was just having to filter out the overabundance of data and the information, and just simplifying the map so it wasn't overwhelming for the viewers. Yeah.
Great. Yeah, it's challenging.
Yeah.
Wonderful. Thank you so much. The 2 final speakers will be presenting back to back because they will be discussing different components of the same project, and the first flows really nicely into the second. The first speaker of the pair is Meg Dupuy-Todd. Meg is a manager at the Environmental Defense Fund, focused on the organization's work in advancing scientific and policy tools to deliver cleaner air and healthier communities. Meg has led projects as part of EDF's Global Clean Air Initiative, including collaborations with Google's Project AirView in London and Salt Lake City. Prior to her current role, Meg worked for EDF's Climate Corp group, where she focused on developing and implementing new program trainings and building relationships with partners to expand impact. The second speaker will be Lauren Padilla. Lauren is an environmental data scientist and exposure modeler at the Environmental Defense Fund. She analyzes geospatial data sets to understand pollution emissions, transport, and exposure patterns in order to reduce toxins in the environment and create healthier communities. She develops tools that lower barriers to large data analysis and that promote open and transparent data for researchers and decision makers. First, let's hear from Meg.
Hi, my name is Meg Dupuy-Todd, and in 2018, the Breathe London pilot was launched with a consortium of leading health and science experts, including our partners with logos pictured here. The project aimed to advance both the science of hyperlocal monitoring and to help people better understand their local air quality, as millions of Londoners face health threats every day from air pollution. We were seeking to better characterize pollution as well as understand the underlying mechanisms in London with advanced data sets, such as the newly collected air pollution data from this pilot and data from our Ways for Cities partnership. So to accomplish these larger goals, the Breathe London project combined both fixed and mobile monitoring and applied new data analytics to map air pollution across the capital. The team of partners measured pollution with 100 lower cost monitors and Google Street View cars equipped with reference grade sensors that you can see pictured in the top photo. We're going to focus on the opportunity that we had with Google to not only analyze the over 40,000 kilometers of total drive coverage during this project, but also how the team used Ways for City data to visualize the relationship between traffic and pollution. And so this project was still active during the beginning of the COVID-19 pandemic, and it was an unfortunate and unwelcome experiment for our team to examine London's changing commuting and pollution patterns. After social distancing was strongly encouraged in the city in mid-March of 2020, monitors in London saw substantial nitrogen dioxide reductions. So in this first figure, you can see the average weekday NO2 pollution pre-lockdown on the left, and compared to a period of time after the measures were in place to the right. The greatest reductions also occurred during daytime hours, especially during rush hour, where we expected traffic to be the highest. And so because road transport is a major source of NO2 pollution, our assumption was there was a link between the fewer vehicles on the road. And through this partnership we had with the Ways for Cities program, we had access to anonymous incident and slowdown information in Greater London. So we were curious to help if that data could help us understand where and how traffic had reduced. And so though Waze data couldn't provide us direct information on the number of vehicles on the road, it had congestion information, which compared speed on the road to free flow traffic. So using Google BigQuery, we were able to analyze large volumes of data to begin to get a picture of the daily traffic congestion in London. On this graph on the bottom of the slide, you can see the sum of the congestion length over a typical weekday on the left compared to a weekday during London's stay-at-home order on the right. And so with our team's analysis, we saw that traffic congestion reduced to such an extent that it was approaching free flow in the vast majority of Greater London roads. And so as the Ways for Cities data and data from the Breathe London project were spatially resolved, we realized we could not only look at these citywide trends, but we could also take a step further and look on the street level to learn more about patterns of pollution. Thank you.
Thanks so much, Meg. So while we didn't show a lot of maps in that presentation, you can really see how the kind of citywide analysis that they did first using the spatial data together in combination. And now we're going to hear from Lauren about how they did more investigation into the more spatially resolved data. So let's all welcome Lauren to all hear from Lauren's talk.
Hello, my name is Lauren Padilla. And we mapped the spatial pattern of daytime NO2 concentrations by taking the median over the full monitoring period about 1 year from September 2018 to October 2019, on every street divided up into about 30-meter long sections. High concentrations are seen throughout the city on major roads in orange, red, pink, and purple, including inside of central London, where an ultra-low emissions zone policy had recently taken effect and actually improved the vehicle emissions standard there. The more times that we visited a location with the Street View cars, the higher confidence we have in the median measurement there, which is why we are showing only segments with at least 5 visits by the cars. This bounded the error to within roughly a factor of 2 or less, meaning that this is a good representation of relative differences between the streets. Then, with the Waze data, we mapped the percentage of time that each street was congested between about May and October 2019. That's when we had the Waze data. The red areas that you see were in jams, as defined by Waze, over 40% of the time in that period. Comparing the maps, we can see that some of the most congested streets are also the most polluted with NO2. Congestion actually changes the intensity of emissions and generally leads to more pollution per gallon of fuel burned. So for the same number of vehicles driving in free flow and congested states, the congested vehicles will generate more total pollution and thus have higher pollution concentrations than those in free flow. It's also interesting to see in these maps, not just where concentrations are high and congestion is high, but where concentrations are high and congestion is low. This would suggest to air quality analysts to look at other potential emission sources not related to traffic jams. The underlying issue could be related to the type of vehicle driving there, like a more polluting diesel truck or bus, rather than the congestion, or even non-transport emissions like building heating or construction could be a factor in those locations. We relied on many of the Google Cloud resources to generate these visualizations. For the Waze analysis, we started by using Cloud Scheduler to trigger a cloud function that saves the Waze feed every 10 minutes into storage. From there, we read the data into BigQuery and parsed and aggregated it as needed for final results that were ready to be mapped in BigQuery's GeoViz or downloaded for additional offline analysis and visualization using, for example, tools like Python, R, Arc, or QGIS. Digging into the queries a bit more, some of the key elements for us were string and geography functions. As Waze users know, the jams data includes a line geometry detailing the jam down to the intersections. Before we could spatially aggregate the jams, we had to split up those line segments into their component vertices using regular expressions on the well-known text of the geometry. Next, we geohashed the points, rounding them to a regular grid so that we could take statistics over time, like the average jam level or the percentage of time in the jams at every geohash. And finally, we reversed the geohashes back to latitudes and longitudes for mapping. The full version of our air quality findings in London are captured in a blueprint for other cities interested in monitoring pollution with these novel technologies. We also created a detailed technical report on the project, and we have shared our Waze processing approach in the Waze for Cities webinar series. And this work has further motivated us to embark on a new project this year targeting congestion emissions more directly. And in that project, we are looking forward to advancing spatial analysis of Waze data, not just in London, but more major cities. You can download the Breathe London Partner Reports to learn more about this pilot and follow EDF's work at globalcleanair.org. Thanks.
Thanks so much to both Meg and Lauren. So there's 2 of you, but I'm going to start with one question and maybe save my second question for later in the Q&A, because I know we have some live questions in the Q&A below. I'll start with my question that I thought of when I read this, and I'm curious to hear more, and for the audience to hear more. I think this is one of the first times that the Waze for City data was used for this kind of air quality analysis, and how combined with this kind of street level hyperlocal air quality analysis, which kind of matched the hyperlocal of the Waze City data. How did London and the stakeholders in the city and the region find it useful? Have there been other cities too, besides London, that that you know of that have combined air quality data, and how did they use it for policy or for understanding their city better?
Thanks, Karen. I can take this one. The researchers who we have shared this with in London, I think, have found it really interesting to see where the most congestion is occurring, and it gives them some clues into what could be the sources of the ambient pollution that we measure. The maps are also a really strong visual reminder of something that I think that all air quality scientists know, but it's nice to see it, is that it's not just the vehicle types or the engine technologies that create intense emissions. It's also how those vehicles are operated, how they're driving. Are they in stop and go? Is it congestion? And then as far as other analyses, so we have plans to do similar analyses actually in other major cities around the world as EDF. We have seen a lot of time series analyses coming out of other groups with the Waze data, but I haven't really seen mapping of the long-term average Waze concentrations quite in this way before. Yeah. As far as the time series, one example to look at might be the Inter-American Development Bank. They did a really nice presentation in the Ways for Cities webinar series, and they looked at time series of congestions in many Latin America cities during times of COVID restrictions.
Fascinating. What was that group again?
The IDB group.
Okay, great. Maybe we'll put a link to that webinar in the down below, resources down below.
Yeah, I'm sure they'd love to hear from you. They were really open about sharing their, recipes for the analyses too. And they had paired Waze with satellite patterns of air pollution, similar to one of the lightning talks that we saw earlier.
Awesome. I have other questions about, the complexities and efficiencies of using BigQuery GIS, but maybe I'll save that for one question later. And welcome. Thank you guys again. Thank you so much for those great lightning talks. And welcome everybody back on the screen because we're going to start taking live Q&A. And I see that we have a couple of questions. So please, whoever's listening out there, please feel free to add your questions. And you can have it be big blue sky or very specific. There's no wrong question. All of them are good. So the very first question I'm going to start with is the first question that was populated in the Q&A from Philip Worrell about LiDAR technology. And it was focused on Michael Heimbinder's talk, but it can be for anybody. And Michael, I'm curious if you do have anything to add or anything to say about LiDAR technology. I can definitely say something, but just curious if you or anybody else has anything to answer to the question, have you used LiDAR technology to help examine and map air quality at a large citywide or regional scale? So Michael, have you done that? Maybe you give you the first shot.
I have not. One of the things that I think is really important that's happening with LiDAR in cities is taking temperatures. And because in New York City, people just don't often consider the fact that most of the people who die from natural disasters in New York City are actually dying from heat. And so 100+ people every year in New York City, for instance, die because they don't have access to cooling centers, they don't have air conditioning, so you can really see with LiDAR and other remote sensing technologies the differences in temperatures across cities. And more we're seeing that when you map temperatures and you map trees, what you see is low-income communities of color have fewer trees, a higher urban heat island index, and are therefore suffering because they also don't have things like access to air conditioning and cooling centers. So I think it's really important, the combining of that type of data and using it to inform especially heat vulnerability.
Yeah, I agree with you there. Is there anybody, I could say more, but I want to hear from you guys. Is there anybody from the panel that wants to add to that? Okay, great. I was going to take that opportunity to mute and tell my children who are doing homeschooling to be a little more quieter, but I'll do that later. So the only thing I'll add is exactly following on what you said, Michael, and kind of piggybacking on Christina's presentation, is that adding different data and what Lauren alluded to, adding different data to air quality measurements will give you will allow you to ask different questions and new questions. And so LiDAR data could absolutely be, in a city like Denver, where elevation is really important. You may not need something as high resolution as LiDAR. Maybe you could use SRTM or other data sets. But understanding LiDAR and like building heights and designs also may be interesting to understand how air quality might move through a city. So a lot of different data sets are useful. LiDAR data. Well, I guess we could say more, but that's another conversation. Let's keep going to more questions. Thank you for that question, Philip. Okay, for Cristina, great job. Yay. This is a question from Gabriel Kotler. A question, what are the pollutants that can be analyzed with Sentinel-5P by means of the applications that you built? And how can they be compared with ground level data? Big question, but see if you can take a crack at it. You can do it.
Thank you for the question. Sentinel-5P measures a few gases, a few pollutants, if you want to say pollutants, but there are a few gases that are being measured in the air column. One of them is NO2, so nitrogen dioxide, you've got sulfur dioxide, you have carbon monoxide, you have aerosols, different types of particles that have been measured, and I think ozone levels as well. So there are a few gases that are being measured with Sentinel-5P. Now, I'm not an atmospheric scientist again, so I'm not very sure how these gases are all being monitored. So for this application specifically, I enlisted the help of somebody that is doing atmospheric science, just to validate that what we're doing is correct. Also because we've used it in another example for the Romanian platform, in which we wanted to provide some information about Bucharest and some areas in Romania that were affected by lockdown and wanted to compare. So I'm not very sure on how to measure that, but we did do another experiment with Sentinel-5P and air quality sensors for educational purposes in ESA, so the European Space Agency, and we had some measurements on ground using this Arduino sensor, and we added different sensor on it. We built like a custom kit. We sent it to schools throughout Italy. We built like a platform for them to do like measurements at school or at home if they wanted. And in the end, we displayed them against what Sentinel-5P is doing. So obviously, the measurement won't be coinciding because you're measuring at the ground and then the satellite is sampling in the air column. But you can definitely see some sorts of correlations. You can see how different sensors measure in different points. So there are a lot of interesting applications that you can do with both IoT sensors and also satellite measurements.
Fantastic. Thank you. Wow, great. Okay, so the next question, and we can always come back to any of these questions if any of the panelists want to add to an answer to one of the questions. The next question, I think I'll skip down and come back, but to Cristina, but skip to Berge. Awesome work. Were the air quality mobile sensing routes optimized for any particular objectives besides sampling at communities of interest and also in areas where there were gaps in static sensor network?
Yes. So on top of those two, the routes are specifically designed to give the low-cost sensors on board a wide range of the concentrations we're looking to test them for. So if a sensor had a particular pollutant it sampled, we look for routes and areas and times that we believed would give them a good variety of low to high concentrations to test its range out, and different pollutant types as well. So the routes are specifically designed, let's say if we wanted ozone, we would go use this particular route for that sensors testing. If we wanted a particulate matter, we were looking for more congested highways or hyperlocal areas with high congestion. So yes, on top of those two, we were looking to give the low-cost sensors on board a very good test on their concentration ranges.
Fantastic, thank you. Great. So the next question I'll ask is for anyone who wants to answer it, and I think that Berge and Megan, Lauren, and any one of you would have something to say about this as well. Are air quality measurements made in the middle of the street representative of the urban areas immediately around them? Is it reasonable to assume that this data is useful for exposure assessment? And that question is from Mohammed Ayub. So hello, Mohammed.
That's a great question, Mohammed. Thanks. So that's something we're also very interested in. And it's a great point. They are representative of mostly, road center lines, and there is attenuation that we've measured and we can model. And part of Breathe London was a major modeling exercise as well, where you can see those concentrations as you approach the sidewalk and the building facade where people are going to be living and working. That the attenuation can be. I'm not going to throw out a number. There's plenty of literature on this. It depends on the topography as well. But I do think they're relevant because these distance decay functions are well established. So you can infer from a road centerline concentration, what it would be further away. And also people, they are driving in the streets. There's a question of actually what is the exposure when you're in the vehicle or on the bicycle or, on the motorcycle. So yes, I do think they're relevant, but I think you have to be careful about the interpretation. It's a really good point to keep in mind.
Thanks, Lauren. Anyone else want to add to that?
Yeah, to add to that, you also want it to be lengthy. Like you can't take just a single day's worth of data and assume that is, usually the typical pollution levels and things like that. So combined with that, you want the time aspect of maybe a few weeks worth of data looking at, to combine the spatial and temporal ends of things to get a general idea of the pollutant concentrations around the area.
Wonderful. Yep. Anybody else?
I would just add, it's representative of what, I guess would be the first question, because if you're looking at personal exposures, it's absolutely representative of that person's exposures. But if you're trying to say, is this representative for the region, obviously you'd have a very different approach. But we've seen with the air beams that, measurements are different when you're in the middle of the road, in the bike lane, right next to the building. When you go up, in elevation, your elevation profile, you're going to see differences depending on how the streetscape is built. And so, there's dramatic differences sometimes in some instances. And it also matters what pollutant you're measuring. You're going to have higher variability for something like PM than you would for ozone. But I think the first question is really representative of what, and that really depends on what type of question you're trying to answer.
That's wonderful. Good answers. Okay, great. Let's see. Maybe we'll come back to one of the questions that was added earlier for Cristina. Could you share the libraries and list of tools that you're using and that are useful, especially concerning the Python and the Geospatial and Earth Engine collabs, et cetera?
So I use multiple tools. It's basically a mash of a lot of things. It's not one single library, so there are many people that actually work. It's a very, very active community. There is a lot of support on a Google forum. So basically, you just need to sign up there. I'm going to give Karen all the links probably that I can find, so you can get it in the follow-up email. But there is a support forum for Google Earth Engine. Professor Qixing Wu, I hope I'm pronouncing his name correctly. He develops a lot on top of Google Earth Engine, and especially to translating to Python. He also has a very nice recent tool on converting JavaScript to Python. So if you have any JavaScript code, you can automatically convert it to Python, which is extremely handy. I use Google Colab, which is widely available. And as for my GitHub right now, what I'm doing, so the code for the application itself is freely available. I have a link to GitHub, but the code that I'm developing right now, unfortunately, I cannot yet release it just because it's for my my personal PhD. So it's a little bit under some licenses, but the idea is that it will be available in the end. So if anybody would like to build on top of it at the end of my PhD, then I will make it available. It's not a problem. But I have a lot of links to give to you, Karen, if it's necessary for everybody. So
that's great. Well, maybe at the end of your PhD, we can invite you back and you can, do a hands-on workshop for some of these toolkits. So that's great. Yeah. Perfect. All right. Let's see. Another question we have is for anyone. It looks like it's from Tim Dye at TD Environmental Services. Let's imagine that it's 2025. What do you envision mobile monitoring of air quality in cities will look like? 2025. So 4 years. Anyone want to take that?
I'll take a guess. I think that cities are going to start rolling out kind of low-cost, more hyper-local networks, kind of like what you're seeing that South Coast AQMD has done. I think South Coast AQMD is doing kind of cutting-edge work in this realm. California is way ahead of the rest of the country with Assembly Bill 617 with community monitoring. And so I think it's going to become common for cities to have their own kind of hyper-local networks of fixed monitors that they use to inform people. And I think that increasingly air quality is going to become like weather data, where people are looking it up every day, checking it throughout the day, and using it to make decisions.
If I could add a little more, so as you're talking 4 years in the future. So at that point, AQSpec has evaluated quite a lot of low-cost sensors on vehicles. So even consumers, individuals can purchase and start populating, putting sensors on their vehicles. So I can imagine hyperlocal data becoming a lot more populated because consumers will be doing it, as well as, like Michael said, companies and fleets will start incorporating it onto their vehicles. So we'll be seeing a lot more populated data in those areas.
I also think we'll see more fleet vehicle use for the mobile. I think China has been a leader in this area already. We'll see more Chinese cities like Hangzhou expanding the mobile sensing.
I can add something related to satellites. So because I come from this area, I think it's going to be much more synergy between sensors, ground sensors and satellites, because the ground sampling resolution for satellites is lower. It's actually getting higher, not lowering, but it's getting higher. So what right now is being sampled at 7 kilometers or something like that gets to 100 meters, 50 meters and so on. And there are many, many companies that go into this. You've got Canadian companies, American companies that are developing sensors to ground sample very, very finely. So I think it's going to be a bigger synergy between the two types of measurements and definitely improving predictions.
I guess one additional comment from the low-cost sensor perspective. I think an increase in mobile monitoring will also give us the opportunity to explore how we can use mobile monitoring to improve data quality from stationary networks. So I think that's something we'll see explored in the next 4 years as well.
Fascinating. Yeah, I agree. That'll be interesting. I mean, what would be great is that if all this data was just magically talking to each other, right? I mean, if there was, sometimes on my team, we talk about from the cloud to the ground, to the ground to the cloud. It's like really everything is there and kind of working and like in your example, calibrating each other. Anyone else? Fantastic. Okay, so we have one more question, and then I will maybe add up, allow if you guys have any burning questions to ask each other, but you also know where to find each other, so you can ask later as well. The question from the audience, and if anybody's watching and wants to get their last question in, please do so. Probably have time for one more after this one. This is for anyone from RSA Blay. I would love to know more about the latest technologies and possibilities concerning 3D height measuring and rendering density point clouds and dynamic trajectories and potential vertical dimensions. Okay, so this is, I'll take it first and then we can open it up to the whole panel. There's definitely a lot of work to be done, especially in Earth Engine with the three-dimensional imagery and image cubes. I know we're not talking about height and point clouds here. That's more of the LiDAR and another direction in that direction. But if we're talking about 3 dimensions here, there are lots of imagery assets in Earth Engine that can be utilized to look at a 3D environment, at least when it comes to atmospheric data and air quality data from satellites. There are also some great work that I know academics are doing, looking at 3D research around where air quality measurements are taken. And Michael, you alluded to a little bit, like the kind of understanding the differences in air quality at the top of a building, on the roof or different stories versus on the ground, on the sidewalk or on road. So there is a lot of applications around 3D point clouds and heights analysis. It's not just as an input into air quality modeling, but also just as to understand the effects of air quality at different heights. But is there anything that people would like to add to that answer around 3D heights and point clouds? Oh, before I open it up, I should say that we also have people already looking for resources and examples and case studies for RSA and we'll put those as an answer to the Q&A question after the broadcast as well. But before I go on, let's open it up to you all on the panel. Any feedback on that question?
Yeah, the only air quality application I can think of in terms of monitoring in 3D has been in Guangzhou, China. Actually, they did mount sensors on UAVs, and so you're flying around and capturing the pollution in 3 dimensions. Also, EDF has done some work again with UAVs sampling like methane emissions around oil and gas facilities. So that can generate kind of more of a point cloud, but it's still sort of a linear trajectory in 3 dimensions as opposed to something broadcast where you get the whole cube filled in. And then there's also 3-dimensional air quality, atmospheric dynamic and chemistry models that would generate that kind of data that can enrich in what you're able to monitor.
Wonderful. Thank you, Lauren.
If I may allow, actually the way the satellites measure different concentrations of gas, it's in the air column, so you got vertical measurements. So you're going to sample the atmosphere at different layers. So that's generating already some sort of 3D structure of the measurement. And this is Sentinel-5E, for example, has different measurements for different kinds of layers. And if you get yourself to know the data and you manage to get to the raw data or to the level 1 data, you can actually play with those different measurements opposed to what is available right now in Google Earth Engine or any other application, whereas gridded data, so it's already been processed and it's fed in a different to show the top or the averaged concentration. So there is data that goes on 3D. It just needs to be processed differently.
Great, thank you, Cristina. Wonderful. Well, I had said that we had time for one more question, but I do think that we're at about 58 minutes now, and this might be a nice time to close. But before I do, is there any final parting thoughts or questions that you guys want to follow up on with each other?
I had a question for Berge. So I didn't realize that South Coast AQMD was doing evaluations of mobile instruments that are vehicle mounted. And considering the number of companies that are doing that type of work, why did South Coast AQMD decide to do that work? And kind of how do you deal with companies who have a lot of intellectual property that they don't want to share when you're trying to evaluate an instrument?
Well, we haven't just yet. So since the Google collaboration project we did, we've actually built our own more optimized kind of specialized version of the mobile platform. So we're actually in development at the moment, but we envision in the future to be able to expand our evaluation process to be able to do on vehicle evaluations as well, and basically extend our AQSpec program into the mobile aspect of it. So not just yet, but it's heavily interested. Yeah.
Awesome. Great. All right. Well, thank you all for joining today's session. To the panelists, thank you very much for your time and preparation and recording this and then being here today for the live Q&A. And for everyone out there for joining us live, and for all of you future on-demand listeners, hello. We appreciate all of the questions. Thank you very much for asking the questions. I hope this session was helpful to everyone out there for your current and future projects. And I hope that you'll join us again for next month lightning round, which will be the theme of crisis response. So hope to see you then. Thanks and have a great day.
Thank you, Karen.